Page 79. You've got a nice box summary that gives you your general confidence interval for a proportion P. Coming up with a confidence interval estimate rather than just a single guess. That margin of error is what we're going to focus on at the beginning today, and move that to be a conservative margin of error and show you where that 1 over square root of n really came from, that you learned as a 95% margin of error before. The margin of error is going to be calculated based on z star, so how confident you want to be will affect that width of your interval, and also the standard error. And the standard error term remembers that p hat, 1 minus p hat over the n is on the bottom. So two things that you have to choose as a researcher: what sample size will I take, and how confident do I want to be? And those two things affect the accuracy of your confidence interval in the sense of how wide or how narrow it will be. So on page 80, we want to take that margin of error and look at it a little more closely. I said there's z star there, which you decide up in front. Do I want to be 95% confident or 99% confident? There's the sample size, which you have to pick in advance too. But there's also p hat in that standard error. And that standard error is an estimate of the standard deviation. It's based on the data, and it's only estimating what that average distance might be. Sometimes that estimate might be close to the true standard deviation. Sometimes that estimate's going to be off. In other words, that standard error part could either be bigger than the standard deviation or it could be too small. And I don't run into too many problems when it's a little bit bigger, because then my interval's a little wider than maybe I need it to be, but it will definitely be 95% level of confidence. But if my standard error ends up underestimating the variability, underestimates that standard deviation, then my interval's smaller than it should be. It really should be this wide, and it's only this wide. So really I might be only 89% confident instead of 95% confident. And I don't want to run into that problem. So a conservative approach is to replace the p hat in that standard error with 1/2. And that's because if you were to graph the function that looks like that part that depends on the data, p hat versus that function p hat 1 minus p hat, what does that look like? P hat goes from 0 to 1. Right? Sample proportions from 0 to 1. When it's at 0, you get 0 times 1, so that's still 0. If you take it all the way to the other extreme at 1, you put in 1 here. 1 times 0 is 0. And if you put in some other values, it turns out to be a quadratic. Not drawing it all that great to scale, but the highest it ever could be is when p hat takes on the value of 1/2. In other words, that standard error does have a maximum. And so if I set it at the maximum, then I'm never going to be underestimating the standard deviation. I might possibly be overestimating it, which is always a conservative way to go, though. Your interval might be a little wider than it needs to be, but it certainly won't err on the underestimating side. So that's what we do. We take 1/2 for p hat, plug it in the two places, and I still got my z star out front, still got that sample size. So here's what the conservative margin of error looks like. Still putting in z star there, got that 2 on the bottom that came out from the 1/2, and that square root of n. That gives you an alternative confidence interval called the conservative one rather than the general one. And what does happen when you put in 2 for z star? The 2 cancels with the 1 on the bottom, and you get back to that 1 over square root of n. So the 1 over square root of n that you learned from chapters 3 and 4 is really the 95% conservative margin of error. And we know that z star is not exactly 2 anymore. It's really what for 95%? Do you remember that from last time? 1.96 is the exact value. So an approximate conservative 95% margin of error is 1 over square root of n. But that's sometimes easier to remember than the z star and having to put in p hat, 1 minus p hat, and do that more complicated formula. It also now doesn't depend on the data, which means if I design a survey with lots of questions, the proportion of people who say yes to the first question will likely be different than the proportion of people who say yes to the second one because they're different questions, different p hats. But as a whole, that whole survey can have an attached margin of error with that conservative version because it doesn't depend on the p hat. And it will work for any of those questions with that same sample size. So you have two formulas now, the conservative one and the general one. They're both on your formula card. And in an exam or on a homework, we'll ask you for specifically the conservative version if that's what we want you to do. The conservative version here has a z star in it because it allows you to be 90% confident or 99% if you wish. If you were doing a 95% conservative confidence interval, I will accept 1 over square root of n as the margin of error that you use because that still works, putting in that 2. Now, one of the nice features about the margin of error being conservative is that it doesn't depend on the data. So now I can use it to answer those common questions you get as a consultant. I want to design a survey. How many people do I need to go ask my questions of? What sample size do I need? How many animals do I need in my study to be able to meet certain requirements, certain conditions? And for estimating a proportion, we can use this conservative margin of error and solve for the sample size. So let's call that conservative margin of error just m. M is your desired or margin of error that you wish to have. Solve for the sample size. It's just a little bit of algebra. And now you have an expression that says, tell me how confident you want to be, z star. Tell me what margin of error you want associated with your estimates. And then I can come back and tell you what sample size you need to be able to attain those levels of accuracy. So here, this sample size formula is also on your yellow card. And this is the one place I do want you to round. And you always round up. Because what we're solving for here is the minimum sample size you need to make sure your interval has a certain margin of error with a certain level of confidence. And anything larger than that will work. It might make your interval a little bit more narrow. So it's the minimum sample size, and if it's not a whole number, and you are going to go out and take that sample size, it's got to be a whole number. So you round up. Means, averages, expected values, those can be decimal form, even if they're for a discrete variable that only has certain numbers that are possible, but sample size has to be a whole number. All right, so let's try it out. We've got an example on the next page. This is looking at Coke versus Pepsi, where a poll was conducted in Canada for Canadian college students, trying to estimate P. P, again, is the population proportion, the proportion of all Canadian college students who prefer Coke over Pepsi, trying to estimate P. So they take their survey results and they create a confidence interval for that proportion. The confidence interval is a 95% conservative version, and it's already calculated for us. It goes from 62 to 70%. So we would estimate right now, with 95% confidence, that the proportion of Canadian college students who prefer Coke over Pepsi is somewhere between 62 and 70%. I'll give you that interval with 95% confidence because what do we know about the procedure that was used to make that interval? If they repeated this study many times, getting lots of different confidence intervals, like the one we just got, what do you know about those intervals? Each one interval either contains the true proportion or it doesn't, but as a collection, 95% of them do contain the true proportion. All right, we're asked to come back and give the margin of error that's associated with this interval. I think we highlighted that last class. Whenever you have the interval, you've got two things that you can get right from it. You can get your best guess, which must be that midpoint, and then you can get your margin of error. This interval was made with the conservative formula, p hat plus or minus, and it had a z star, 2 square root of n. So p hat has to be that midpoint of that interval. And then the margin of error, if I were to try to calculate it with the formula, I wouldn't get very far because I don't know the sample size. But I would be able to get it from that interval because The margin of error is what you went out each way. So your interval is actually like the full width, which is twice the margin of error. All right, so the midpoint here is going to be what? First, let's find p hat, which is the midpoint. If you need to work it out, you can add up the two endpoints and divide by 2. 0.66 is the middle. So there must have been 66% of the sample that said yes, they prefer Coke over Pepsi. And 66% is what I started with, and I went up to 70 and down to 62. So what's my margin of error? Plus or minus 4%. That's the half width of my interval. So the margin of error could be the distance from 70% minus the 66%, or from 62 to 66, or just take the full width of the interval, which is 8% width, and cut it in half, and you've got your margin of error directly. Every interval can be used to find back the best guess and then the margin of error, even if you don't have the details of the study in terms of the sample size. All right, margin of error is 4% here. If they wanted the margin of error to be less, 3%, and they still want it to be 95% confident, they come and ask you, how many people would we need to survey? And that's our question in part B. What sample size is needed? If I want to make a 95% confidence interval, so there's my level of confidence, and I want the margin of error to be 3% instead of 4%, which it was in the actual study. So our formula card, we're looking at the second page. So at some point you want to start working with that, especially with homework number 3. Basically that one section there on proportions. And the sample size formula that we looked at on the previous page is also laid out there for us. So don't have to try to memorize that. You do, you might forget something in there or put it in the wrong place. And as we solve this question, I'll show you a couple of the common mistakes that are made by students. One mistake is what they put in for Z star. Some people will put in 0.95 or 95 because it's 95% confidence. But I need the multiplier that has the 95% in the middle. And what is that multiplier? Two answers that I would accept would be 2. I would use 2 and accept that, or the exact value of 1.96. You can look up your Z star from table A2 that we highlighted. Table A2 at the bottom, look at the infinite row under the 95% level of confidence. You can remember 1.96 because we use that a lot, and it will come up a bit on your homework too. And again, I would have accepted though 2 because I'll always accept that for 95% in the middle. Another common mistake, won't be so much here. What do we put in for M? M is your margin of error that's desired, so that would be 0.03. Some of the old exams might say width of 6% because they defined the formula in terms of the width, 2m being the W. So you might see that old formula somewhere. Students that read the question and it says plus or minus 3% might put in 3. But it has to be on the proportion scale, so it needs to be 0.03. And then what's something else that I don't want to forget to continue? To make sure I square. We'll get a 3267 underneath. About 1067.1 is my final answer here, but what will I put on the final answer line? For how many students do you need at least? 1068. At least 1068. Now what would happen if you put in the 2? You'll get a slightly larger value, which is still at least 1068, so it works. And I would have then sort of 2 correct answers for rounding up to the nearest integer, whether you use the 2 or the 1.96. You have a similar question on your homework. This will help you with question 4 for homework number 3. want you to take a look at part C, give you about 30 seconds to read it through and think of what your answer might be. And that's our one clicker question for today if we don't get to the last one by the end of class. So you have some choices there for what's going to happen if we repeat this survey in the United States. Think about C, and we'll click in your answer here in a moment. And as a little bit of a guidance, I have written out the formula one more time. That is for the confidence interval. The poll is going to be repeated in the United States. Bigger population, 10 times as big, roughly. And 4 times as many people will be interviewed in this particular study. So they're asking how the corresponding 95% confidence interval is going to be compared to the other one that was for the Canadian poll. Will it be twice as wide, half as wide, 1/4, 1/10, the same width? Now, when you interview those United States college students, you might get a different p-hat, right? It may not be the same 66% because it's for a different population. Does p-hat affect the width of the interval, though? No? Just that margin of error part. Z-stars going to change or not? Nope, still 95%. So think of the only thing that's changing. What's going to happen? All right, B and C seem to be the most popular choices. And this time the majority do win. That is the correct answer. Why is that the case? It's nice. Does the size of the population make a difference? Does the fact that the United States population is 10 times bigger than the Canadian one? No. Most students think that that should still affect the accuracy. If the population's large, and I take my sample, as long as my sample is representative of that population, it's the sample size that I'm getting my information from. The sample size is what dictates the accuracy here. And instead of having a sample size n, I'm going to have a sample size 4 times n. 4 times as many. And the square root of 4 is 2, so that's basically going to cut that whole margin of error in half. The n is going to be replaced by 4 times n, but it's under the square root, so you don't gain 1 for 1, you gain by the factor of the square root. So it'll be half as wide. The population being bigger does not make it less accurate. My sample size is larger, and it's not 10 times larger, it's just 4 times larger, but it's still going to have a smaller margin of error. Once the population is large, taking that sample, just make sure you have a random sample, representative, and you'll have a good picture of what's going on. All right, what if I wanted to cut my margin of error by 1/4? How many more? What factor do I need for my sample size? 16. Needed 16 times as many observations to cut it by 1/4. All right. Using confidence intervals, coming up next. So these are the 2 formulas that are on your yellow card. What is not on your formula card are these 2 conditions. But to make the confidence interval, you need to have a random sample, and your sample size needs to be large enough. The large enough rule is that at least 10 rule. And since all I have is my data, in your data, did you see at least 10 say yes and at least 10 say no? That's what you have to check. Then your sample size is large enough. The using of the confidence intervals to make decisions is highlighted in the last section of Chapter 10. We're going to highlight two principles right here. The second one we can't do until a little later. Principle number one we've been using already. Your confidence interval is this range of reasonable values. The confidence interval we had for the Canadian college students went from 62 to 70%. Any of those values in there is reasonable, values I would accept and say, yes, that could be the population proportion. Would you say that 80% is reasonable, though? Could they claim that 80% of the college students in Canada prefer Coke over Pepsi? Our interval was centered at 66%. Going out each way only gave us a maximum possibility of 70%. 80% would have to be rejected. 68% would be accepted. 69% would. Anything in the range that's there is accepted. Anything that's outside is rejected. We'll use that for doing some hypothesis testing, actually, by seeing if the value's in the interval or not. And then the third principle has to do with when you have two intervals for two different population proportions. Suppose you were going to break up the Canadian college students into male versus female students to see if they have the same preferences in terms of Coke over Pepsi. Look at the interval for males, look at the interval for females. And if they overlap in any way, then there are values that are in common that they could both have as that population proportion. So you'd have to say there's no significant difference. If they are distinct and do not overlap, then you'd have evidence of a significant difference between the rate for men versus the rate for women. So making each confidence interval, looking at the range of reasonable values, showing a significant difference if the overlapping is not there. They do not overlap. A couple ways to use these confidence intervals. Let's try it out with a very simple example for the Canadian college students that we were working with. And it simply asks, would Coke be able to advertise that a majority of Canadian college students prefer Coke over Pepsi? Based on the study that was based on a decent sample size, representative, the interval goes from 62 to 70%. Would you be able to say you have a majority? Yes or no? Yes. And your reason would be why? Not that 50% is not in the interval, but the entire interval is above. The entire interval is above 50%. It's not just that 66%, your sample proportion is higher than 50. It's that the entire interval is above 50%. So our answer would be yes. All the values in the interval are greater than 0.50. The entire interval is above the 50% mark. It's possible to have 53% in your sample, but the interval goes a little bit below. And if it is, then you don't have significant evidence from a statistics viewpoint. All right. We are turning to Chapter 12 for the rest of today. The other side of inference. To highlight Chapter 12, I want you to think about what we just decided a minute ago. We're going to start writing out things like this. H0, HA. Those are hypotheses, theories that we want to test. And we just tested a theory. Do we have a majority? The alternative hypothesis is usually the researcher's theory that they want to put to the test, their claim. Do I have a majority? Is that population proportion, P, greater than what? Greater than 50%. That first H0 or H0 is this null theory, the status quo, which would say you don't have a majority. And we've used data now to decide whether we have to say with no majority or we do have majority, and the data supported this hypothesis HA. There are 5 basic steps for doing a formal testing of a theory compared to what a confidence interval does, which is giving you an estimate, a range of reasonable values, acceptable values overall. Those 5 basic steps. You first have to set up those theories. What is it that you want to test? I want to test that the new drug is better, more effective than the standard drug. I want to test that this new teaching method is more effective for students to retain learning in the long term. There'll be conditions to be met before you can go ahead and summarize your data. The word statistic means you took a summary of your sample. We're going to take our sample and summarize it in a statistic, and it's called a test statistic because you're using it to do a test, to test a theory. We'll have to find this thing called a p-value. P-value is a probability value, so it's going to be using probability, that allows us to decide whether the evidence is convincing or not. It basically says, well, take that status quo and compare your data to it and see if you can reject it or not. The p-value will allow us to decide if our results are statistically significant. Have any of you ever heard that phrase before? Stat sig, statistically significant? Sometimes in the article they'll say there was a difference, but it was not significant. Means it was not statistically different. And then we'll write up a conclusion. So today we're going to formally go through step 1 and try that out a few times. And then we'll get through at least one full example of all 5 of these steps together. And setting up the hypotheses, though, is the first step. You have to know what it is you're testing before you can perform that test. Null hypothesis and alternative. H0HA. The null hypothesis is a statement that there is no effect. That new treatment is not any better. There is no relationship between those 2 variables. There's no difference. Sometimes it's called the status quo, that says there is no change. The alternative is the thing that states something is going on, that there is an effect, and that is usually what the researcher is trying to support. I mean, they have invested their time to study this new drug because they think it's going to be a better drug in helping cure some disease. There's also going to be a direction of extreme that we'll be seeing in the alternative. And everything that we're setting up here are statements about the population, not statements about the sample, because the sample I can see whether there's an effect or not, but in the population. So let's try it out. Our first example, page 84, is about left-handedness. We stated before about 10% of the population is left-handed. We have a researcher who thinks that artists are more likely to be left-handed than the general population. And we're asked to set up the theories that would be tested for that researcher's claim. So the researcher is studying what kind of population? Population of all artists. Here are all artists. And in that population is a ball for each artist, and whether they are left-handed or right-handed. And it's a very large population. And what I'm trying to learn about for that population is the proportion of artists that are left-handed. Now, how would I represent the proportion for a population? What symbol do I use? Proportions are either P or P hat. Which one is for the population? P. So let's let P be the population proportion of all artists that are left-handed. That's the parameter that I'm trying to learn about. It's the proportion of all artists that are left-handed, that population rate. And now that I've defined it, I don't have to write that phrase out each time, and I can just state the theories in terms of that parameter. It's usually easier to state the alternative first, because that's the researcher's claim. The researcher's claim is what? That the proportion of artists that are left-handed should be what compared to that 10%? It should be higher or greater. The status quo would be what? That being an artist makes no difference. That the rate of left-handedness would be about still 10%, the same. Now we could write the alternative as greater than and the null as less than or equal to. And that's how your textbook starts to write it out. H naught is that it's not more likely. It's either 10% or less. The alternative is that it is more likely to be left-handed if you're an artist. But the idea is I'm going to compare my data to 10%. 10% is the value that I'm going to compare my data to see if I'm definitely larger than it. So really the equal always has to go in H naught. And you could write H naught with only the equal sign, because that's the only value I have to concern myself with to show that I am indeed bigger than it. All right, the direction is always going to be based on HA. We're looking for values that are big, too big, bigger than 10%. So the direction is said to be a one-sided test, one-sided to the right, to the larger values. So what if I took my sample of artists and it turned out that in that sample only 8% were left-handed? Would you stay with H naught or would you reject H naught and go with that new theory? You would stay with H naught. You didn't support that new theory at all. What if my sample ended up having 12% that were left-handed? Now, is there some evidence for that theory? 12 is bigger than 10, but is it significantly bigger is what we have to establish. Some of those distances will not look that big, but they will be significant because they were based on a huge sample size. Some of those distances will not be that big because they were not based on enough data to show that difference. So we'll be looking at the data relative to that 10% and deciding if we're significantly larger. All right, there's one example. Let's try the next one. We're now looking at a pharmaceutical company, and they claim that for this new medication, the proportion of people who would experience a side effect would be less than that standard, which has been 20%. So they're studying people who have and take this new medicine. Let's define our parameter of interest here. We're talking about proportions or percents. P is always going to be the population proportion. And what should I continue with here? The population proportion of all patients taking the new medicine that what? What outcome am I going to count here that have side effects? The proportion of all patients taking the new medication that experience side effects. That's the quantity I'm trying to learn about, the parameter. So defining it once allows me to more easily set up my theories in terms of that. The claim is that the rate of side effects should be less than 20%. That's the claim that's being put to the test that goes in HA. How can we write out the status quo? Status quo would be that there is not an improvement, that the rate of side effects is either greater than or equal to 20. And again, it's only the equal that I have to put there. The greater than part really is being tested, but I'm going to take my data and compare it to 20. If I show I'm less than 20, won't I be showing that I'm less than 21 or 22 or anything that's larger? So I don't need the larger part in the H naught, but I always have to have the equal part there. And the equal part will allow me to take one number as a frame of reference and compare my data to it. What kind of direction do we have here? The direction, again, is in the alternative. This is another one-sided test, but one-sided to the left, to the lower values. And that direction will be how I'm going to shade an area that's going to be called the p-value and calculate that probability. All right, those are the two different possible directions for specifically looking for larger or smaller. We have one last one to show you all three possibilities. And this one is based on a census report that said 48% of all households have no children. We want to learn to see if that rate is still applicable today. So we're going to take a nice large random sample of 500 households. to see if the population rate has changed from that 0.48. So P, again, is going to be defined. It's actually right in our words here. It's the population proportion of all households, today that have what attribute? They have no children in residence. What's the status quo? What would be the prevailing viewpoint under the assumption that there's been no change? The value of P should still be 48%, 0.48. That's the status quo. Statement of no change, that it's still 48% like the census reported a few years back. The alternative is looking for what here? I want to know if it's changed. Is it different? Is it bigger or smaller? So the alternative here can be written as, is it different from 0.48? This is not a one-sided direction, but rather a two-sided. I want to know if there's a change. I don't have a preconceived notion of that it's gone up or that it's gone down. I just want to know if it's different. This is what a lot of companies do. They have target levels that they are maintaining, and they monitor the process to see if things have changed from it in either direction. A two-sided version. So those are the three possibilities for what the alternative will look like, one-sided or two-sided. There are always statements about the same value P. P hat never goes in H naught or HA. You're not theorizing or hypothesizing about the sample. You're theorizing about the population. You're going to use the sample to decide between those two theories. All right. So where are we going? You have to make a decision between those two theories. It's kind of like that in a jury trial. Let's parallel it with that idea. So according to a jury trial, the defendant is said to be what? Up front. They should be innocent until proven guilty. So H naught, the status quo, should be the prevailing viewpoint. What we should have is that the defendant is innocent. HA would be that the defendant is guilty, not innocent. And the evidence comes in. And you assume first innocent, and then you look at the evidence and say, oh, that's kind of unusual if really they're innocent. There seems to be strong support for the alternative theory, and if it's beyond a reasonable doubt, you go and claim that they are guilty. Same idea for making decisions in statistical hypothesis testing. We're going to pretend the H naught, the null hypothesis, is true. We start out with the status quo. We pretend there's no difference. The data comes in, and we look at it and say, is it likely to have come under that theory or unlikely? Is it likely or unlikely? We will measure the probability of getting what we got in our data under the null hypothesis. And that probability is called a p-value. So here is what we'll be doing. We have to decide between our two theories. We'll take our data. It'll always be assumed to be a random sample. We'll look at that data graphically to make sure it's okay to summarize, but we'll calculate eventually what is called a test statistic. The first test statistic we're going to see is a z statistic. We already have calculated z-scores. We'll eventually calculate some t statistics, some f's, some x squareds a little later. They will all be some measure of how close the data is to the null. We'll pretend the null is true and compare the data to it, and use that information to make our decision. We'll calculate a probability based on that test statistic. It's called the p-value. Here's the formal definition of a p-value. Assume the null hypothesis is true, have that model in mind, and then calculate how likely it is to see the data you got under that model. What if it's really likely to see what you got in your data under that H naught model? Well, then you'll probably stay with H0. It's very compatible. What if you calculate this probability, this p-value, and find out that seeing what you got would be like hardly ever going to happen under this H0 model? Well, then I don't think H0 is true anymore. I would reject it. Didn't we do that with the example of saying people voted when they really didn't? We had a 39% rate as a model, and we found that 56% saying that they really voted was really unusual under that model, like would hardly ever occur. So we rejected, we either knew that 39% was wrong then, or else something else was going on in that study. The p-value will measure your compatibility with H0. It measures how compatible the data are with H0. It's always going to be a probability, so it's a number between 0 and 1. And what we have to decide is then what kind of values will tell us to stay with H0 versus reject. If the data is likely under H0, you stay with H0. So if the p-value is big, you stay with H0. If the p-value that we calculate is very small, the smaller it is, the more evidence against H0 and in favor of your alternative. If this p-value is really tiny, then it says your data would hardly ever happen under H0. So if your data doesn't look like it comes from H0, and that is the data you got from your population, then you're going to reject H0 because it's much more likely to come from the alternative instead. The smaller the p-value, the stronger the evidence against H0. In fact, we usually set up a particular rule for defining when you decide to reject H0, and you reject H0 if your p-value is small enough, less than or equal to some cutoff value, and that borderline or cutoff value has a name. It's called the significance level. And our new Greek letter to represent that level is called alpha. If the p-value is small, you reject the null. If the p-value is small enough, how small? Less than or equal to some number that you pick up front. Usually you pick about 5%, kind of like that 95% level of confidence. In fact, many of you have probably been told to do tests and just look at the p-value and see if it's less than 5%. And if it is, you can write down it's statistically significant. Well, we're going to show you why that makes sense. If the result turns out to be a p-value that's small enough, we say the results are statistically significant. Statistically significant takes a long time to write out. So I see a lot of students write it as stat sig, which is okay. Common levels of significance will be 0.01, 0.05, and maybe 10%. If you decide to do a test at a 5% significance, you're saying that the data needs to be so unusual under the null theory that you would see it happening less than 5% of the time if H0 is true. That's how unusual it has to be before you'll be convinced to go with the alternative. If you want to be more convinced, then pick alpha to be 1%. And then if the data is showing that unlikeliness, you go with the HA. So those are some of the basic ideas and some definitions. There's going to be two possible decisions at the end. Page 85 has those two possibilities. The bottom, either the p-value is small, so we can reject that null, and we have significance, or it's not. We often say fail to reject H0 rather than accept H0, because that's what we're doing. We're comparing the data to H0, and either we can't refute it or we can. And we'll write up a conclusion. So it's a lot easier to go through an actual problem, so we're going to do that. We'll set up this test statistic and try out going through one problem. I think I have, because we need it right now, a couple change-ups here. Ready to try a little more on the hidden meanings? That's a 1 in a million. 1 in a million. What's that letter? H. You're going from H H2O. 1 in a million. I did not get that one. It took me a long time. All right. Bear with me for a little longer. Chapter 12, Section 3. A little more on the setup. And then we get to try an actual problem out. Setting up the hypotheses is step number 1. If you don't set those up correctly, the rest of the problem's wrong. This is what you're trying to put to the test. We just did 3 examples. We did the left-handed artist, we did the side effect rate for new medicine, and the households with no children to show examples. We're going to write here those generic hypotheses. They're always about P, the population proportion. If you're writing out an H0 and an HA on your homework or on an exam coming up, it's going to be about a population proportion. We theorize whether that population proportion is going to be larger, smaller, or different from some value. In the artists, we thought it would be more likely that they would be left-handed, so it was greater than 10%. In the side effect rate, it was, is it going to be smaller? Less than would be better. And then we always had a number that went on the next part. 10% for artists, 20% for the side effect rate, and we need a way of generically representing that value. So we write it as P with a little naught to represent that null value, because that's the value that you put in H0 and say it is that value. It hasn't changed from it. So H0 is always the equal. You can write H0 as the complete complement of the HA if you want to, for those first 2, but the equal always is in H0 because I'm comparing my data to the 10% rate to see if the artists are bigger than that for their rate. So equal always goes in H0. There'll be a value that sits next to it. It'll be in the problem. We think that artists are more likely to be left-handed, so it's higher than 10%. The 10%'s in the problem that you put there. But right now that just stands for that value generically. So P0 is just the null or hypothesized value. It comes from the particular study, the particular scenario or situation. It'll be a number that's given in the problem. It's sometimes called the null value or the status quo value. We said that we're going to make our decision between the 2 theories by first pretending H0's true. So we're going to say, let's say H0's true. So the true proportion P is this particular value. And then we're going to look at our data and compare it to that value. So under H0, the true value of P is known. It's some specific value. We'll take our data and get a sample proportion. And here's one of your homework questions, actually. Question number 1 is very much like what we're going to write out here. What do we know about sample proportions, P hats? It's a statistic. It comes from your sample. And if you took another sample the same size, it's going to be a different answer because it's a random quantity. It varies. What is the distribution of P hat? If you take a large enough sample size, what do you get? We did it for the counts, and we've done it for the proportions. The model for P hat will be approximately normal. Sample proportions vary normally around, what are they centered at again? The true proportion, P. And and proportions vary with a certain standard deviation. And that true standard deviation was P1 minus P over N. That's called the sampling distribution of P hat. It tells you how the sample proportions vary. So that's what you're asked to characterize on your first question on homework 3. Gives you a scenario, and in that question it tells you the value of P. Suppose the true P is, and then you can draw that model or express that model. Now in hypothesis testing, we still don't know what this model is going to look like because we don't know the true value of P, but under H0 we do. If H0 is true, we have the value of P. So I can actually draw a picture of this normal curve. So we can put in P0 under H0 being true. And then I would have the normal model I could draw, and I would be able to actually calculate my test statistic. So what makes sense here? You're trying to learn about what the true value of P is. Is the true proportion 10% or greater than 10%? You've got a sample, and your sample rate turned out to be 12%. So that's bigger than 10, but I need to figure out how much bigger than 10 is it. I'll take my sample proportion, and I'll compare it to that null value. How far apart are they? Obviously, a big answer would have some more support than a small answer. But I need to look at that distance relative to the yardstick, the standard deviation. I'm calculating a z-score. A z-score is always found by taking your observation minus the mean divided by the standard deviation. And the mean is the true proportion P, which under H0 is that number. And there's the true standard deviation, if H0 is true. So now I've got a z-score. And when you think of a z, what kind of model do you think of? Still normal? But which particular normal model? The normal 0, 1. The one that's on table A1. Approximately a standard normal or normal 0, 1. Which means I can use my table A1 to find probabilities underneath it. And that's how we'll find our p-value. So let's turn to an actual problem. Let's do that one for the last few minutes today. Put some actual values in here. Let's solve the left-handed artist problem. Let's put that theory to the test. So you can already do step 1. We did it just 5 or 10 minutes ago. 10% in the population are left-handed in general. Researcher speculates that artists are more likely to be left-handed. Wants to put that theory to the test. Takes a sample of 150 artists. 18 turned out to be left-handed. So what would I want to look at here? Not just the 18, but 18 out of 150, which happens to be 12%. And what would that quantity be? Is that P or is that P hat? I just calculated the proportion of artists that are left-handed in my sample, so it's P hat. So I'm kind of just looking at my data ahead of time here. And I want to put this theory to the test that artists are more likely to be left-handed. The hypotheses that the researcher wants to test are about the parameter P. P again represents the population proportion of all artists that are left-handed. The theories to be tested, H0 is the status quo. Being an artist makes no difference, has no effect. So what should that rate of left-handedness for the artist population be? If there really was no difference from the general population, it should still be 10%. The researcher's theory or claim is that that rate would be higher, more likely. And we're doing a one-sided test. Now, why can't I just stop here and say, it's obvious I've proven HA true? 12% in your sample were left-handed. That's bigger than 10%. What happens if you were to take another sample of 150 artists? Are you going to get 12% every single time being left-handed? Maybe the next time you get 9%. And then maybe you get exactly 10%. Maybe you get 13%. It's going to vary. So we have to understand how it varies to know whether 12 and 10 are really different or not. The fact that 12% is what I got in my sample tells me it makes sense to go on and do the test. If I had gotten 10% or 9% or 8% or anything smaller, I wouldn't need to really go on and do the test, because there's no way I'm going to support the alternative theory with those kinds of values. But here there is some evidence. Now, the test can be done only if a couple conditions are met. The first condition is the standard one. You have to have a representative sample from your population, or it doesn't make sense to proceed. We were told that we have a random sample of artists. We can extend the results to the population of artists like our sample represents. The other check is that at least 10 rule. At least 10 yeses and at least 10 nos. But here I have to check it with P naught and not P hat. The at least 10 rule is checked under H naught. Would you expect at least 10 left-handed people and at least 10 right-handed people? This is under H naught. So let's try that checkout. Our sample size is 150. That looks pretty large. If H naught were true, which is what we're going to have as a base, then what should be the rate of left-handedness? It should be 10%. That's the null value. And under H naught, we would expect 15 left-handed people in our sample. Under H naught, we would expect the remaining 135 to be right-handed. This is the expected number of left-handed people in my sample. And that's at least 10, and so is the other one. I know I observed 18 in my sample that were left-handed, but that's not going to be enough. It has to be that under H naught, you would expect at least 10 of each type. 150 seems to be kind of large, but that 10% was a little small, but it still makes the cut here. So we can do our test. So what are we going to do? We're going to take our sample proportion, which was 18 out of 150, 12%, and I want to see how far away it really is from 10%. I'm trying to learn, is the true rate more than 10%? My data comes in at 12%. Is that bigger? Yeah, it's bigger by 2% difference. But is that a significant difference? Well, let's measure it in terms of the right yardstick. And that right standard deviation would be using the 10%. I'm standardizing my data. I'm comparing it to the null theory. I'm pretending H naught's true. So this should be the mean, and this should be the standard deviation, and seeing whether 12% looks unusual or somewhat compatible. On top, we've got a 2% difference. The denominator, or standard deviation, would be about 2.5%, 2.45. So my test statistic value is only about 0.82. How far away is 12% from 10%? It's not even 1 standard deviation above 10. It's 0.82 standard deviations above the 10%. So does that look like it's kind of compatible with the 10% or really different from 10? Somewhat compatible. 1 standard deviation, you get 68% in there. It's not till your 2 or 3 standard deviations that you're starting to be somewhat in the tails and sort of unusual. So we're going to convert this 0.82, this measure of distance, to this thing called a p-value. Let's calculate our p-value and finish out our problem. All journal articles report the p-value because they're not all doing z-tests. They're doing t-tests, they're doing some other kinds of tests. But if you get it back to the p-value, everyone can take that p-value and see if it's going to tell you to reject or stay with H naught. The p-value is this probability of seeing your data under H0, of getting a test statistic as large or even larger than the one that we observed. The p-value says how likely is it to get your test statistic, which was a z, in this case as large as we did get, which was 0.82, or even larger. I ask you, how likely is it getting your data under H0? How likely is it to get a z of 0.82? And under a normal curve, a z of 0.82 is just a single line, a point. And you can't get an area there, a probability. So you have to do as extreme or more extreme. 0.82 is somewhat large, but is it really large enough? Can you find this probability? Is that one of those basic ones we learned how to do with table A1? I want the area to the right of 0.82. Your table's back on page 56 of your lecture notes. Or maybe you brought that table with you. Now your table gives you areas to the left, and I want an area to the right. So if you look up the 0.82, that answer that you get will not be your final answer. You'll have to do the complement. I'll need to do 1 minus whatever that value was, which was how much? 0.7939 from table A1, which gives me a p-value of 2061. If H0 were really true, if there really was no difference in the left-handed rate for artists, then we would see the results that we got, or more extreme, a little more than 20% of the time. It would happen fairly often, about 1 in 5. That's not very unusual. That happens often. We take this p-value, and if this p-value is small, that tells you your data does not look consistent with H0 at all. If the data is consistent with H0 in any amount here, like 20%, then we're not going to refute H0. P-value here is considered large. The most common level of significance is 5%. We decide to reject H0 if the p-value is small enough. Since our p-value of 20%, 0.2061, is larger than the significance level that was selected, 5%, we stay with H0. We cannot refute H0. We fail to reject. That null hypothesis. That means the results were not significant. They were not statistically significant. 12% was higher than 10%, but it was not significantly higher when you use statistics and that idea of variability. So if we were writing out a conclusion about artists and this researcher's theory, do we have enough evidence to say researchers are more, or artists are more likely to be left-handed? Did we have enough evidence to say that? No. There is not sufficient evidence to say artists are more likely to be left-handed. Not enough evidence to support that theory. Two possible conclusions: we either have enough evidence to say what we wanted to say, or we didn't. There's our first full example. All day on Tuesday, more testing of theories. So hold off on that homework 3 at the end.